All right, we have a wire. A wire with a mass of 1 gram per centimeter. So guys, you know what? Here's what I'm going to say. The length of my wire is going to be 1 centimeter, which by the way, 1 centimeter is 0.01 meters. So what's the mass of my wire then? 1 gram, which is going to be 0.001 kilograms. So our L is 0.01. The mass is 0.001. Now, did you have to choose these numbers? Absolutely not. You could have said that the length of your wire was 1 meter. And if it were 1 meter, well, 1 meter is 100 centimeters, so that'd be 1 meter, and then this would be 0.1 kilograms. It doesn't matter what length you choose, because they're giving you mass per length. Okay, so let's just go with this. Now, here's a top view of the tabletop. So they tell us that the current is running, let's see, the wire carries a current 1.5 amps eastwards. Let's write that down. So current here is 1.5 amps running eastward. So here's north, south, east, west. Okay? So the current's running east, and it moves, the wire is moving horizontally to the north, which means, which way is the force on the wire? The force has to be north, right? The force on the wire is that way. So with this information, we can use right-hand rule number 1 to figure out which way the magnetic field must be going. And remember, we're looking down. It's like you're standing above the table and you're looking down on the table. So do right-hand rule number 1. Your thumb is the current. The palm of your hand is the force. Which way are the 4 fingers going? Straight into the table, which is like vertically downward. So the magnetic field, the B field, the B field is vertically down. You guys down with that? The B field is vertically downwards, like X. The X here represents the B field. X is in, okay? All right, now, how do we find the value of the magnetic field? Well, dudes, the first thing is we got to find out what the force is required to move this wire. So we go, okay, force is equal, the force is going to be equal, like, let's see. Let's do a side view now. Here we go. So here's the tabletop. Here's the table right here. We're going to do a side view. So this guy, this represents the wire right there. Like we're looking at the side of it, right? All right. So there's the force of the magnetic field, FB, is pushing the wire to the north. And then what is the other way? Friction, because they mentioned that there's friction here. What can we assume? They don't explicitly say it in the problem, but we're going to assume that the wire moves with no acceleration. So basically, the force of the magnetic field is equal to friction, which is equal to mu Fn. So we have mg down, normal force up, like that. So what has to be true? Normal force and mg are equal. So the force of the magnetic field is going to be mu, Fn is mg, so we get mu mg. So we got mu is right here, 0.2. So plug that in there. Mu is 0.2, m is 0.001, and then g is 9.8. So when you plug all those values in, we get force of magnetic field equal to 0.00196 newtons. All right, so now with that, we can figure out what the magnetic field must be. Okay, so what equation is for force on a wire? Force of magnetic field is BIL sine theta. What's the theta in this situation? 90, because look, the current's going that way, magnetic field's into the page. The angle between to the right and in is 90. So this goes to 1. So now B is going to equal FB over IL. So the force of the magnetic field is 0.00196 newtons. The current is 1.5 amps. And then the length is, we already have the length right there. The length is 0.01 meter. And this gives us an answer of 0.13 Tesla. So the final answer is 0.13 Tesla directly down, vertically downward. Now look, as I said, could you have chosen a different length for the wire? Yeah, and you'll get the exact same answer. Exact same.